start with phase diagram. So phase diagrams allow us to organize knowledge that we have about materials in a graphical way. And over here, for example, in this schematic, you can see the phase diagram of iron. You're probably familiar with it. So it's pressure and temperature. And you can see the different phases. So phase center cubic, body center cubic, hexagonal close packed, and so on, liquid over here. And you can also see the paramagnetic and ferromagnetic states. So in general, the phase is going to change when the pressure changes or the volume or the temperature changes. So the important keywords to remember are structure, magnetism, volume, and temperature. So in thermodynamic equilibrium, at constant pressure, nature likes to minimize the Helmholtz free energy. And it looks like a simple equation, but there is a lot that is packed in here. So it includes the potential energy, the kinetic energy. So potential energy is related to the arrangement of the atoms. The kinetic energy is going to be related to the temperature and how fast the atoms oscillate. And for the most part, I think the energetic contributions are well understood. The entropic contributions are more difficult. So they depend on the number of possible arrangements and also the average kinetic energy of the system. So this is a fight, I guess, between entropy trying to be at a maximum and energy trying to be at a minimum. And we have the first and the second law of thermodynamics at play. It's a heavy equation. Okay. Sorry about that. So if we had all this information, we could design materials from scratch using computers. And this is the motivation of a lot of people, governments, companies. So if you need new material for construction, just specify what you need, and then the computer will give it to you. Okay, I'm going to keep this one small. Reality is a little bit different. So here we have experimental phase diagrams of iron. The one on the left is at low pressure or relatively low pressure. And the one on the right, you can see the triple point of iron. And this is more or less how it looks up to 350 GPa, which is what you will encounter in the inner core of the Earth and at temperatures of 6,000 Kelvin. And you can see that there is definitely some variation between the experimental results. The melt from HCP varies by as much as 25 GPa between experiments. So these are difficult experiments. This is a slide that I stole from Brent. So, but it's really nice to visualize graphically the different contributions to the entropy. So we have the configurational entropy, which is actually very small. Most of the entropy is going to be in the dynamics, so how the atoms move, and the interactions, especially at high temperature, are going to contribute quite a bit. So phonon-phonon interactions, electron-phonon interactions. Entropy plays a critical role. So here I have a diagram. So this is a study of 508 polymorphic organic molecules. And the structure was computed without entropy and then with entropy. And in the yellow region, you can see the structures that actually change, switch sign. So not including the entropy will have or predicts the incorrect structure. And here's some more. So in a sample of 29,902 entries for inorganic crystalline materials in the materials project database, about 50% of them are within 15 MeV per atom of the ground state. So this can be considered metastable materials. So changing the temperature might change the structure. Perhaps more importantly, because of all of these things that we don't quite know, it's possible that we don't even know what is the structure of iron close to the Earth's core. So to focus the mind a little bit, I'm going to ask you this question. And I'm not going to quite give you the answer today, but is the crystal structure of iron in the Earth's inner core body center cubic? So over here we have phonon dispersions. So I'm going to be talking about the information that we can get from them. Basically, you can see that everything is positive or not imaginary. And this comes from density functional theory, molecular dynamics, spin polarized calculations at 1043 Kelvin. And everything looks all right. The phonon modes over here, like at N, for example, they correspond to particular displacement patterns. So this will be the longitudinal mode at N. And this one will be the, I guess, one of the modes at H. So each of these points is going to be related to a particular displacement pattern, and it's going to have a particular energy. So phonons are real as far as we can tell. We can measure them. So over here we have aluminum. So one of the first measurements by Brockhaus, who kind of invented triple axis spectrometry to measure these dispersions. And you can see over here to the right, we have vanadium. So as you increase the temperature, this is 84 Kelvin, you can probably not see it. The one at the bottom is 493 Kelvin. And so it becomes a little wider, and it even starts to have like a kink over here. So these distributions will be cuts along a particular wave vector. The other interesting thing about dispersions is that if you aggregate everything and get a histogram of the number of phonons that you have per energy bin, you will get a curve that looks like this one. This is work by Lisa Mager, another CDAC student. And so over here, you can see the density of states at 300 Kelvin. And the vibrational entropy can be estimated using the density of states. So it is the integral of the density of states and then some function. This function looks like a curve, kind of like an exponential going down, and it's at a higher value at low energy. And so low energy vibrations have more entropy. Maybe you can see it as, you know, they move very slowly, and they occupy a big space, physical space, and then the ones that move very quickly, they don't occupy as much space. At least that's one way I think about them. So as you might imagine, a lot of work has been done on iron. This is a paper from 2002. And essentially, they play around with the value of the spin. So when the spin is 2.2 or magnetons, then the dispersions look all right, and they agree pretty well with experiments. But when they decrease the magnetic moment, or the spin, this mode over here becomes imaginary, and this one over here also. So it seems like this one is more sensitive to the magnetism. So when I have a lot of letters over here, a lot of words. This is my own literature review. But the important thing is that when those modes become imaginary, the structure is mechanically unstable. So it will not be able to support itself, and it will collapse into a different structure. So this is work by Vocatlo, Alpha, and others from 2003. In this paper, they argue that they argue pretty strongly that it's possible that BCC is stable at inner core temperatures and pressures. This part is not up for discussion too much, though. So as the pressure increases, so 40 GPa, 80 GPa, 115 GPa, you can start to see how the photon dispersions change. So over here, it becomes slightly imaginary at 180 GPa. And so the structure will be unstable at this point. They continue increasing the pressure. So this is 260, 210, 250 GPa. And even though they don't show the imaginary modes, you can see that they are becoming stronger. So the magnitude is increasing. This is work by Leonov et al. It's a little bit more recent, so only 10 years old. And what they do here is that they consider the magnetism at a finite temperature, and they have some method to get to above the Curie temperature. So this is about 1.2 times the Curie temperature. And without the magnetism, the structure is collapsed. So this will be, I can see if I can show it over here. It will be this phase over here. So still alpha, but paramagnetic. So with the magnetism, it looks okay. Without the magnetism, it collapses. And this is work from 2015. And they use this method called scale. And this is at 5,000, 6,000, and 7,000 Kelvin and 360 GPa. These are non-spin polarized calculations. And what you can see is that with increasing temperature, that mode from gamma to n that was imaginary before becomes real. And so this doesn't mean that BCC is going to be the structure, but it means that it's not mechanically unstable. So it could at least, in theory, be. So in this paper from 2010, Luo et al., they calculated the phase diagram of a potential BCC phase between 185 GPa and 385. So the red is the melt, the green is where the BCC could exist or will exist, and the blue dots or the blue diamonds, the phase is unstable. And again, they just did that considering the photon dispersions. Okay, so I'm going to talk a little bit about, should have removed these ones. The harmonic ensemble lattice dynamics and a Gaussian process regression using graph kernel similarity. So this is work that we have done in my group. So the harmonic ensemble lattice dynamic, we essentially very manually implemented the von Karman model, but we get the force constants from molecular dynamics calculations. So the BVK model essentially is a generalization of Hooke's law for 3 dimensions, at least in its most simple simplest presentation. So over here we have the force. So the magnitude of the force felt by an atom I in the direction of A is the sum of the products of the displacements of every other atom and their respective force constants. So in principle, they can go to as many nearest neighbors as you want. In practice, we usually cap it at 5 nearest neighbors or something similar. So we use the displacements and the net force as calculated from density functional theory molecular dynamics. And over here, we have the symmetry constrained force constants. So for third nearest neighbors, some of them are going to be 0, they cannot exist, or they're going to be equal. And so that symmetry decreases the number of force constants that you have to compute. So I think for fifth nearest neighbors, BCC is like 15 or so force constants. So we have the displacements over here from the molecular dynamics, and we also have the forces. So we just have to solve this matrix, and we get the force constants. So what we do is that we solve that matrix for every time step, and just have to make sure that you have enough atoms so that that matrix is over-specified. And then we put all the dispersions on top of each other. So this is like basically a 2-dimensional histogram. So you can see that now these lines have some finite line width, and the line width changes with temperature, with pressure. So they resemble experimentally measured photon dispersions. So this particular system over here, it's iron, but without the magnetism. So these are non-spin polarized calculations. We have 188 atoms in this supercell. So it's relatively big for DFT, but really tiny to get many of the effects that we would like to know or to understand well. So something that you can see maybe is that without magnetism, we have some dispersions here that come from gamma, and they're just imaginary. Over here, some of them go up and then go down into the imaginary regime. So these are basically, this is an unstable structure. And so this agrees with these calculations. So you need the magnetism for the BCC structure to be stable. Here we have kind of the same thing, but at a higher pressure and temperature. So this is 2.76 angstroms, 2.755. So this is about 7 or so GPa, and about, well, I guess from 1700 Kelvin, 1850, and 1950. So actually, if you go into the details of the DFT molecular dynamics, things get kind of nasty pretty quickly. So you can see here how we had some trouble maintaining the temperature. Well, here it is oscillating. It is not horrible, but the oscillations are kind of big, and the pressure sometimes drops, sometimes it is maintained. So this is for 2.755 angstroms and 1950 Kelvin. This is 2.76 angstroms, 1850 Kelvin. So we have different ones. So it is difficult. If you have more atoms, then it is easier to converge the temperature. The oscillations are going to be smaller. But for DFT, that is pretty tough. Still, most papers that you read are going to report like an average of the temperature. So since machine learning algorithm doesn't care too much what the temperature or the volume is, we decided to just let it go. We explored different regions. So over here, the green dots, it's BCC, and the brown ones are FCC. So we just decided to explore this whole region. So what you can see is that at high pressure and temperature, there are more modes, especially this one, 2/3 in the direction of gamma to H, that become imaginary, and they are related to whether they want to go into HCP or FCC, so the different paths. So the other way that we can use our code is, instead of getting the force constants and the dispersions for every time step, we can just put everything, all the time steps in the same matrix, and then solve for that matrix, and then that is identical to all the elements TDEP. So these results that I have over here are TDEP, but they were computed using our code. So this is at pretty high pressure. So this is 2.49 angstrom, 2.39. So this is closer to the 300 GPa. And they go from 800 Kelvin to 5,000 Kelvin or so. So you can see that on the left, the 2.49, all the dispersions as calculated by TDEP are positive or real. That is not the case if you compute them step by step, and that might be an issue with doing it step by step, or it might be something that actually has physical meaning, and I'm not sure which one it is yet. This is a higher pressure, 2.39 angstrom, and so you can see that these modes become imaginary. So the structure is unstable. This is at 800 Kelvin. When you increase the temperature, the structure becomes stable again. This is the previous one, 2.39, and here's another one, 2.36. And you can see that you require a higher temperature to stabilize the structure. So over here, we can compare our results with the ones from Luo. And so we came up with a similar phase diagram. Our methodology, using quantum espresso rather than VASP, and using TDEP rather than scaled, produces this phase diagram. So the stability, mechanical stability region is higher than the one, or larger, predicted by than the one predicted by Luo. But we also see that instability at low enough temperature. And we have the instability over here as well for the FCC. So all those data points, so this is work by Valeria, the one that I just presented. And she used all the time that we had on the nurse computers. But I didn't care too much because we were building a data set to use with machine learning. So this is work by Adrián de la Rocha and in collaboration with Bert de Jong from Berkeley Lab and Yuhang Tang. So we use this way. So we have a graph. Actually, well, so first I'm going to talk about why graphs are important or desirable. When you have a mirror image, for example, here or here, then A traditional machine learning algorithm will have a very hard time because the input stream will be very different, but the answer should be the same. The energy or the forces just like switched. And so people have been trying to implement these symmetries into the neural networks or the machine learning models themselves. But using a graph takes care of that naturally. So there's this marginalized graph kernel. So we have over here methane or something. And so the atom types and the bond types, so I guess this is chlorine, correspond to nodes and edges in the graph. So one way that we can calculate how similar one graph is to another is by performing a random walk. And this is not very different from PageRank, the method that Google initially used to rank pages. So you can throw a dart and land on a molecule or an atom randomly. And then from there, you traverse the graph many times. So how long is your path is determined probabilistically. And how many times you do it, you can set that up. So if a molecule is better connected than another one, or an atom, then you're going to have a larger probability of traversing that molecule. So by calculating the paths of different lengths, we can compare the similarity of one molecule to another. So the math looks a little bit like this, and it's pretty tough. So that's why this paper, well, I guess so it's this paper. It generated a lot of interest, but it was difficult to implement it in practice. So Yuhang from Berkeley Lab, he realized that ugly equation can be reformulated kind of like this. So you have several matrices that represent information in the graph. So the degree is to how many other atoms each particular atom is connected. We applied this to a crystal. So initially, or originally, he did it with molecules. So every atom is connected to every other atom. So this degree is kind of meaningless in a way. We're not quite using it. Here is the vertex or the node label. So right now we just have the name of the atom. So it could be iron, it could be vanadium, it could be something else. But you can put other stuff in here. And so what we want to do, what we're trying to do right now, is to put the spin on that particular atom rather than just a label. The adjacency is what is the strength of the connection between the atoms. And so the closer, we have a function here that kind of decays. And so the closer it is to one atom to another, the stronger it's going to be. And the edge label, we currently don't have information there. So as you can see, there's still much more that we can do with this model. So what we actually machine learn is how, well, we have the energy of a configuration. So at a time step, the atoms are slightly displaced from their ideal positions, or very displaced, I guess, depending on the temperature. And the energy is calculated from density functional theory. And we see how a new configuration that we haven't seen before, how similar it is to all the other configurations that we do know, and then assigns an energy. So I'm going to remind you of a few things over here. So first, this is how the BCC structure looks like. So you have so you have your atom in the middle, and you have the 8 ones in the corners. Well, in the corners. This is the FCC, this is the HCP. The harmonic potential looks just like this. And the force is the derivative of the energy with respect to the displacement, so the slope of this, and the direction is opposite to what it is moving. So over here, if this ball moves to the left, it's going to feel a force to the right, and because the slope is negative, so you make it positive. And if it moves to the right, it's going to feel a force to the left. Over here, I have some results about the absolute error in the prediction. And if the displacement is small, so up to actually 0.7 angstrom, so it's pretty big. It is state of the art. So it compares with the best machine learning models that you see in the literature. If you go to 0.8 angstroms, 0.9 angstroms, well, that's kind of outside of your training set, so the error becomes pretty bad. So do not believe these ones, they are outside. But the ones for smaller displacements, they're pretty good. So this is these are the forces, or force versus displacement in non-spin polarized iron at pressure and temperature in the delta phase. So we just grabbed a random, and random was 168 time step, and for each atom in the supercell, we displaced that atom in different directions. We did that for every atom, and then over here we are aggregating the results. So this is in the direction of the first nearest neighbors, so it's the 1, 1, 1. So what you can see is that, as expected, if you move to the left, you get a force to the right, and if you move to the right, you get a force to the left. So this is consistent with Hooke's law. You can see that there is definitely some variation. So those will be the white lines that you see kind of in the background. And since we calculate the energy, we predict the energy, we have to take to get the force, we have to take a difference. So here's just a numerical approximation, and down here there's a polynomial fit. The results look pretty similar. So this one looks a little bit weird, but you can still see that it's positive over here, somewhat negative over here. This distance over here, it goes back to 0. That's an extrapolation. So that will be this atom occupying the place of the neighbor. So that was definitely not in the training set. So you can believe this region, let's say between -4 and 4. So this is what happens when we look at the 100 family of directions. So when the atom moves to the left, then it feels a force to the left. When the atom moves to the right, it feels a force to the right. So this is unstable. So it's actually being pulled out a little bit. And you can see that this is the 100, this one is the 010. And in the 001, there's actually a positive force in the when the atom is supposed to be in their equilibrium position. So the atoms are pulled out or stretched out in the 110 plane, and then they're pushed up in the 001 direction. And we saw these with multiple time steps, multiple simulations or runs. And so there's always one in which you see the positive force, and 2, in which you see the instability. So this is the schematic of the Martensitic phase transition from FCC gamma to BCC alpha. And so here it says that the Martensitic transition occurs by compression of the FCC lattice in the direction 001 and expansion in the direction 110. So the opposite of what we see with the BCC lattice non-magnetic. So what we actually can see is that the BCC wants to transform into FCC because there's no magnetism. So a major effect of magnetism in BCC iron is the stiffening of the secondary neighbors force constants. So obviously, the delta phase exists. So the magnetism must stiffen those force constants in order for the structure to be stable. So this is going to decrease the entropy. So that is kind of bad for the phase stability, but it will be mechanically stable. So that's actually pretty good for its existence. So because we haven't done the analogous calculations, I'm going to switch a little bit to iron vanadium. But iron vanadium is similar to iron. It is BCC based, so it is the B2 structure. But it is ordered, so you have, if you have one vanadium in the center, then the atoms in the corners are going to be iron and vice versa. And rather than being ferromagnetic, it's anti-ferromagnetic. So the spins of the iron and the vanadium point in opposite directions. And this is kind of old work that still has not been published, but I presented last time. So this is using HELP, but it's using classical potential, so classical MD. We have the 2.86 angstrom at 10 Kelvin, and the structure is stable. Everything looks all right. When the lattice parameter is decreased to 2.84, then we have imaginary modes. But when we increase the temperature to 300 Kelvin, they become stable again. And so that is the story that we will see also with iron. So we did 0 Kelvin density functional theory, DFT calculations on the V2 structure. And we saw that it becomes the M5 modes, the same ones that we have over here. They become unstable as the volume is decreased. And that critical lattice parameter is 2.777. So Olmedo was very careful there. And we couldn't quite reproduce the phonon dispersions of Wang et al. But they also predicted an instability. So here we have the equation of state using PBE. The pressure is about 33 GPa for the transition. Using PBE Sol, it's about 12. And so that tells you that because the electronic structure is so complicated for iron vanadium, close to the Fermi level, the functional that you use actually, well, everything matters more than for most materials. So here we have a new way, and I didn't have time to explain it very well. So, but we can compute force constants cheaply at finite temperature. So before we had to run the whole simulation, it uses up all the time. Here, what I'm doing is I start with the ideal lattice or the positions, and then I create phonons of appropriate wave vectors, but the phase is random. And so this kind of simulates real material. And then I pick several different parts of this large structure, and we get the force constants for that, and we average many of them. So we have a kind of like an ensemble. And you can see that over here, so we have the force constants. In order for the structure to be stable, so in order for these phonons to be real, these two force constants, so second nearest neighbors, longitudinal and transverse, they have to be of opposite signs. And that happens here. At 900 Kelvin, it is stable. Okay, so we took 2.77 as a lattice parameter. So that is slightly below the 2.777. That is the critical lattice parameter. And then we actually started from the high temperature and decreased the temperature. So you can see that it is stable, barely, but it is stable at 900 Kelvin. 300 Kelvin, maybe it's arguable. 10 Kelvin, this structure is definitely not stable. When we include the magnetism, so this is without magnetism, these ones are spin polarized. And at 900 Kelvin, the iron vanadium is above its critical temperature. Because there's a lot of movement in this system, it becomes ordered, but it can also have disorder. It goes into some sigma phase. There's a lot of effects in there. It's difficult to know for sure what is the critical temperature, but it's going to be about 500 Kelvin. So at 300 Kelvin, I included the magnetism, and at 10 Kelvin also. And you can see that even though these become a little bit more tenuous compared to not having the magnetism actually stabilizes the phase even at 10 Kelvin, the cubic structure. And so this is the same story as in iron. Both temperature and magnetism help the cubic structure, and it's also similar to titanium, hafnium, zirconium. Even though those are not magnetic, you're going to have hexagonal phase at room temperature, and when you increase the temperature, it becomes cubic. So the work that we did before for iron, even at very high pressures and temperatures, essentially just shows that phase diagram will be similar to the one for zirconium, for example, except that the pressures and the temperatures are much higher. So here I just show, confirm that the temperature stabilizes the V2 structure, and that the magnetism helps stabilize the V2 structure. And we have some ideas of why this is happening. So when we look at the charge, so we haven't looked at the charge with temperature, only with compression. As you compress the ideal structure, charge moves in between the secondary neighbors. So there's like a bit of a pseudo hole in there, and that is probably related to the softening of those force constants and the eventual demise of this structure with these N5 phone modes, because it's easier for them to just continue moving in that direction until they find another ground state. But that we still have to work a little bit more on. So is the crystal structure of iron in the Earth's inner core body-center cubic? I've seen nasty arguments like in reputable journals. I would say probably not, but the BCC structure very likely is mechanically stable. The accurate calculation of allotropic contributions is still somewhat beyond what we can do right now computationally, but perhaps in the next 5 or 10 years, we're going to have a better answer. I think that the magnetism, even at 5,000 Kelvin or so, it might shift a little bit, that region that Luo looked at. And there might be some other interactions that increase the entropy and might make the phase stable. There's still a lot to study over there. So thank you. This work was done by Homero Reyes and Valeria Arteaga, and with my collaborator Ramon Ravelo at UTEP. Thank you.
Thanks very much, Jorge, for a very interesting talk. This is beautiful work. The
Thanks.
Session is open for comments and questions. You can just unmute yourself or use the chat or just speak up.
Hi, Jorge. This is Brent. You covered a lot of ground, really a lot of topics here. I could ask you, there's a number of things that are curious, but I want to understand how you're putting in magnetism at finite temperature. You're just assuming co-alignment of the spins. Is that right? There's not disordered moments, or how are you doing?
Yes.
So that's that's useful.
Yeah, it gives you an idea.
Right.
So what we want to do is, because doing the DFT will be pretty computationally expensive, we can put the disorder moments here in the vertex label, generate phonon dispersions, and then apply a genetic algorithm to find the potential or possible orientations of the spins at finite temperature, and try to do that with DFT afterwards. But yeah, that's definitely a complicated problem.
I haven't seen this reference before. Does it deal with spins directly, or just general features about disorder on the lattice? This graph paper here.
It's completely general.
Okay.
So the methodology was developed by Yuhang Tang from Berkeley Lab, and we applied it to crystals. But it could be, they're using it for not just like physical systems, but like internet and complex systems and things like that. So it's very general.
I may wait till you actually work it out with the spins before reading about it. Thank you.
Yeah. There are some people who say that it cannot be done. We'll see.
Well, thanks, Brent. Philippe, do you want to ask your question? I'll read it then. I would expect iron to be highly anharmonic near the melting temperature. Can this approach still address stability, given that the entropies and energies are assumed to be harmonic in nature? What about anharmonicity?
So which approach? The machine learning, or
I think it would apply to both, because you're just using a single force constant. You're using an effective force constant. And so how well is that capturing the anharmonicity?
If you had a lot of computer time and you create a big enough data set of DFT molecular dynamics, then the machine learning model will definitely account for that anharmonicity if it is included, in the molecular dynamics. Health will definitely have some issues with that, because it is just feeding a harmonic potential. This other method, I'm still thinking about it. So right now the phonons come from harmonic phonons. So if we can, come up with a model of inharmonicity and how that affects the distribution of atoms, then it will work too. But I think that's an exciting problem, but not something that we're going to solve tomorrow.
What if you did the same calculation with ab initio molecular dynamics, that is, at the same level of theory to molecular dynamics and not lattice dynamics?
So these are, okay, so the original data is density functional theory, molecular dynamics, and then we're feeding the force constants. So it assumes the BBK model, but these ones, because it's a machine learning model, it doesn't assume anything. So they include everything that you have in the DFT molecular dynamics.
I see. Okay.
May I ask you a question?
Yeah, of course.
Question about Born conditions for elastic constants.
About what?
Born conditions
Uh-huh.
of stability
Yes.
based on elastic constants. They formulated for different systems. And how important are these conditions, say, relative convex hull construction, say, phonon dispersion? They call it in the paper, original paper, as necessary and sufficient. And I recently calculated several structures in an orthorhombic system, and they both satisfy these conditions, Born conditions. But convex hull construction can segregate this. So what is your take on this conditions compared with the estimates of enthalpy of formation?
So, I can give you an example here. So actually in this paper by Wang, I haven't calculated explicitly the Born conditions, but they get that the shear modulus decreases with pressure, but it stays positive or real. And with the Born conditions, if you have a negative shear modulus, or it becomes 0, then the structure becomes elastically unstable. So what I will say, well, I don't want to say anything that is false, but I think that particular phonon, atomic patterns, they might find local minimum. So you are displacing the atoms from their equilibrium position. And the Born conditions is when everything is just in their equilibrium position. So, I think you add a little bit of the dynamics to the statics, and you might get, that the structure is unstable when heated or when the atoms start to move far enough. So yeah, that'll be my take.
Right. If you calculate monoclinic system and use these conditions, it's very easy to get this negative condition because of negative C35. But at the same time, these systems, they have a excellent phonon dispersion curves, no negative imaginary frequencies. The stable according convex hull construction in the I understand this is just a lack of dynamics.
Yes, I think that's so. Actually, maybe Russ can tell us a little bit. But so we measured iron vanadium, just the crystal structure as a function of pressure, and we couldn't reproduce these. And now we're trying to look at the possible crystal structures that the BCC could move to. And we haven't built the computational, I guess we haven't written the code to get this in like the monoclinic, for example, or like some other structure. But that would be something that probably will be pretty helpful. So it's I agree, would be a good direction.
Thank you for answering.
My pleasure.
Well, I was going to follow up on that. You have done structure search calculations at these same pressures and volumes. So at this point where you have the instability at the endpoint at this pressure or lattice constant, what structures are you finding in the structure search?
Well, so we did the tetragonal, and it is, I guess it's lower, it could be lower energy if the volume is small enough, lower energy than the cubic. And the phonon dispersions were all real. But again, when we started looking at the phonons as a function of the compression, they also become imaginary. So we still have to search more.
Yeah, I see. Okay. Tadashi has a question.
Hi, yeah, thank you for the great the presentation. Can you go to phase diagram?
Which one?
Phase diagram iron, which included some statement about this one. Yeah. So my question, I'm a theoretician, so that it's kind of like a nitpicky question, but epsilon phase HCP is described as a para, right? But this is HCP, so that magnetic state of HCP lattice is supposed to have an ordering, either ferromagnetic or antiferromagnetic. So I wonder that what is a sort of like a source of information that would go to this para. At final temperature, I can imagine that if spin-spin interaction is low, perhaps it's a dynamical para.
Well, this is a schematic, but I don't think I can answer your question because I'm not an expert in epsilon iron. But I do know that for simulations, most of the time, they just don't assume that there's any magnetic moment. And there are some papers that they do look at different spin orientations. But I'm sorry, I cannot answer that question.
Okay. So for your information that for the ambient pressure, my understanding is that this transition from ferro to like a para with a different structure is kind of like experimentally validated by measuring a local magnetic moment as well as a macroscopic one. What it means is that if you see local magnetic moment but not the macroscopic one, that means it has to be para, right? So yes. It seems to me that in theory, this is something that experimentally validated. Just my comment.
Yeah, I think that is correct.
Okay, thank you.
Yeah, that's right. This has been experimentally observed. Mm-hmm. You mentioned the heated debates about the structure of iron in the inner core, and it's true, the debates have been heated. I don't know if they've been nasty, but they've been heated. But the most recent work shows absolutely no evidence for pure iron being BCC at those conditions, work that we did this past year.
Yep, I give it
even up to a terapascal.
Maybe a 5% chance, just to cover my bases.
Well, I think it's an interesting point, though, because what you're trying to argue that there is some kind of mechanical stability. Mm-hmm. I'm not really sure if that's entirely needed, but mechanical instability as opposed to thermodynamic stability. So it could be mechanically stable, but thermodynamically unstable relative to HCP, which is what's seen everywhere in pure iron.
Yes. Mhm.
And then if you start adding impurities, because there are impurities up to 10% in the case of iron in the core, could that stabilize BCC? Those experiments haven't been done.
Question.
I think we cannot rule it out. I think that was kind of my conclusion.
For pure iron, but not necessarily iron in the core, which isn't pure iron. Anyway.
May I ask a question last?
Yeah, go ahead.
Are you suggesting sort of that this high temperature BCC phase may be caused by impurity, as seems to be the case with beryllium?
I think that's a question for you, Russ.
Well, I'm not suggesting that is the case. That experiment hasn't been done, or at least hasn't been done sufficiently well to rule it out. That 10% of some impurity, whether it's silicon or carbon or oxygen or sulfur or some combination, could stabilize BCC.
Thank you for the clarification.
That's my view anyway. More questions, comments? Okay, well, thank you very much, Jorge, for
Thank
giving
you much for the opportunity.
the second talk. It's number 69 in our series. So thank you very much.
Thank you. Thank you, Brent, for the questions, everybody.
Okay, we'll see you next time.